In section 5.1, I'll introduce the concept of force and describe Newton's three laws of motion. In here, in section 5.1, I'm going to introduce the In section 5.1, I'm going to introduce the concept of force and describe Newton's three laws of motion. In this section, you'll see me define force and describe its effects. We'll introduce Newton's three laws of motion. I'm going to give 7 examples of forces that you're going to need to know about. And we're going to demonstrate how to draw something called a free body diagram. So first off, I'm going to define what a force is. A force is an interaction between an agent and an object that will cause a change in the velocity of an object. So if we have an object, here it's a box, the object is the thing that receives the force. And in this case, the box would be the object. The agent is the thing that exerts the force. So the person on the left is obviously an agent. That person is exerting a force on the object. You may think that Julia in the picture here is an agent, but she's not. She's actually exerting a force on the rope. It is the rope that is the agent. That's the thing that's exerting the force on the box. It's important to remember that forces are vector quantities. Their direction matters, and we're going to have to keep track of their direction with positives and negative signs, and we're going to have to worry about the x and the y directions independently. I'm going to briefly describe to you Newton's three laws of motion. Newton's three laws of motion can really be used to describe why everything moves in the way that it does. It is foundational to the rest of everything we're going to talk about for the rest of the year. In 1687, Isaac published his most famous work, and physicists simply refer to this work as Principia. It's the mathematical principles of natural philosophy. He did a lot of things in this book. He laid out his theory of gravitation. He explained a whole bunch of other laws, and he really spelled out these three laws of motion that really explain everything else. And most of modern physics is built on these three ideas. We'll start out with what's known as his second law. That's just an equation. It says the acceleration equals the net force. The net force is just the total force on an object divided by the object's mass. Now, if we concentrate on the special case of the net force on an object being zero, well, acceleration 0 over anything is 0. Zero acceleration implies a constant velocity. And that's what Newton started out talking about with his first law. His first law talks about this special case where there's no force acting on an object, and so the object experiences zero acceleration and experiences constant velocity. His third law that we'll get into in a later unit talks about forces always occurring in pairs. So whenever there's a force of one object on another, the second object always exerts a force back on the first object. Forces always occur in pairs, and these pairs are always equal in magnitude and opposite in direction. So forces are what determines how an object moves, but motion can also imply something about the forces. So if we have an object that is at rest, just sitting there, not moving, or if we have an object that's moving with a constant velocity, and constant velocity looks like an object moving in a straight line with a constant speed, both of these types of motion imply zero acceleration. Zero acceleration implies a zero net or total force acting on an object. This is what we would refer to as Newton's first law. Any situation where we have an object that is at rest or moving with constant velocity, we automatically know that the net force on it is zero, and that's described in Newton's first law of motion. If we have the case where an object's velocity is changing, where it is not constant, and you can recognize a changing velocity if the speed changes by speeding up or slowing down, or if an object changes how it's moving as far as its direction of motion. In that case, there is a non-zero acceleration. There must be a non-zero or unbalanced net force acting on the object, and this is what's described in Newton's second law of motion. And we're going to hit this really in depth in about 2 sections. Over the next few slides, I'm going to provide you some examples of forces that you're likely to see in problems throughout the year. The most common force that we're likely to see is weight. Weight is the force of gravity acting on an object. The thing that exerts that force, the agent, is whatever source of gravity that your object is closest to. Usually the source of gravity for most problems is going to be the Earth. It could be the moon if you're near the moon, but whatever source of gravity the object is near is the agent that is exerting the weight force on your object. The weight force always acts vertically downward. Always, always, always. In fact, that's what we define as vertically downwards, the direction of weight. So when we draw in the force into diagrams, we're going to draw an arrow that points down, and we're going to label it W for weight. The second one is the drag force, and the drag force happens when an object moves through air. Sometimes the drag force is so small that we can ignore it or neglect it, and that should be noted in problems. But as long as we have an object moving through air, you can count on there being a drag force. And the thing that exerts that drag force is the air. And the direction of the drag force is always opposite the motion of the object. So when we draw this into a diagram, we usually need to know what direction the velocity of the object is in. And then we would draw an arrow to indicate the direction of the drag force opposite that velocity vector. The next force that we need to concern ourselves with happens when we have an object that's connected to a string, a rope, a chain, a cord, anything like that. We're going to have the force called tension, and we use a capital letter T to represent the tension force. Obviously, the agent, the thing that exerts that force, is the string or the rope, and the direction of it is always away from the object, parallel with the rope. And it's important to note that if you have a rope that is relaxed or has some slack in it, there's no tension force. The force of tension only happens when we have our string or rope that's taut. And the same rope, if we have multiple ropes, will have different tensions. But if we have only one rope, that rope is going to have the same tension everywhere. And so it's going to pull on both ends of the rope, like you can see in the picture here. We have the tension force that acts on our the box, and you can see that tension force acts up. But we also have that same tension force acting on the man's hand. And a lot of times with tension problems, you're going to see what's called a pulley. A pulley can change the direction of the tension force by changing the orientation of the. All right, the next force that we need to concern ourselves with is an applied force. And this is just a general way to describe some outside force acting on an object. So it's going to be pretty obvious which direction the force is because the applied force is going to be described in the problem. So an example of this is like a person pushing on an object. That person would exert an applied force to the object. The next is thrust, and we're going to use a capital T, lowercase h to represent thrust because T was already taken by tension. So thrust is the force that results when an object actively pushes on air. So the air is the thing that's exerting that force. And some examples of this is like a helicopter blade pushing on the air or a fan pushing on air. The air pushes on the fan, the air pushes on the helicopter blades, and that's the thrust force. Rockets and jet engines also provide a thrust force by pushing on the air and having the air push back on the rocket, back on the jet. That's the thrust force. On this slide, I'm going to talk about the forces that we need to be concerned with when we have surfaces in contact with our object. So the first one is called the normal force. Now, the normal force does not refer to a typical or usual force. Here we're using the word normal as in the mathematical context of normal being perpendicular. So here, the normal is referring to the perpendicular part of the surface force that supports an object that's in contact with the surface. So the surface is what exerts the force on the object, and the normal force is always directed away from the surface and perpendicular to the surface. So the orientation of the surface exerting the normal force is what dictates the direction of that normal force. And the second one is called friction. Now, friction is the most complicated force that we're going to discuss this year. And friction is so complicated, it's going to get its own unit. Next unit, we're going to talk about friction in a lot of depth. And it's complicated because there's several types of friction. Now, friction has one type where the surfaces do not slide past each other. Static friction keeps objects sticking to each other, preventing sliding. And the second happens when there is sliding occurring, and we refer to this as kinetic. Anything that root word kinetic refers to motion, where there's relative motion between the surface and our object. This slide, I'm going to discuss how to draw a free body diagram. Free body diagrams are common tools that help analyze the forces that are acting on an object. They're referred to as free body diagrams because we're going to picture the object as a body that is free from its environment. We only focus on the forces acting on the object and not what it's doing, not what's surrounding it. We're just focusing on the object and the forces that are acting on it. So we're going to draw the object as a dot. You can get more artistic if you want, but generally we just draw it as a dot, sometimes as a box. And the forces are going to be drawn as arrows that are pointing out and away from the dot. So what we don't want to do is draw an arrow pointing into the dot. We don't want to draw it like that. If we want to indicate a force that acts to the right, we would draw it like that. The third step is to worry about the length of the arrows. Now, we don't always have to worry about the length of the arrows. Sometimes that's important, but it does help visualize the forces acting on the object and which forces are stronger. And the length of the arrow is supposed to represent the magnitude or the strength of the forces. So if we have two forces that are acting on an object and one force is stronger, we would draw that the arrow representing the force as longer than the other one. So here in my drawing, the force exerted by B is less than the force exerted by A. Now, like you see here, this step isn't always necessary, but usually we're just concerned with the direction of the forces. Okay, on the next few slides, I'm going to demonstrate how to draw free body diagrams. So in this, we want to draw a free body diagram for a man as he's climbing up a rope, and we're instructed to neglect drag. So first, we'll start by drawing the man as a dot, and we should always worry about the weight force. This is almost like a given, so we can always draw that arrow pointing down labeled W. And because the man is in contact with a rope, we should worry about the tension force. And the tension force, in this case, is going to be pulling the man up. And I drew the tension force as stronger than the weight force because it says he's climbing up. But this may, in fact, be wrong because we don't know if he's climbing up with an increasing speed, a decreasing speed, or a constant speed. And so the relative magnitudes of the tension and the weight force are really unknown, but I'm just making a guess at this point. But really what I'm concentrating on these slides is what's the direction of the forces and drawing those the arrows representing those forces in the correct direction. Okay, on this one, we have a skydiver that's falling downwards. We're going to draw a free body diagram showing the forces acting on her as she falls. So here's the skydiver. And of course, we always have the weight force that acts down. And we're going to have a drag force that's acting up. And the direction of that drag force is determined by the direction of her motion through the air. So the velocity vector points down. And if you ever want to draw in a vector to represent the direction of motion or the direction of the velocity of an object, never connect that arrow to the free body diagram. Free body diagrams only have forces as arrows connected to them. So only forces on a free body diagram, not velocity vectors. All right, here we have a book that's held against a wall by some applied force that's pushing on it horizontally. We're again going to draw a free body diagram. Okay, so here's our book. And of course, we have that applied force pushing to the right on the book. You can see that in the diagram that was given. Of course, we have the weight force that acts down. But now we have to worry about the forces from the surface of the wall. So there's two forces that we always have to worry about. One is going to be the normal force. And the normal force, remember, is perpendicular to the surface of contact. Here we have a vertical surface, and perpendicular to the vertical direction is the horizontal direction. That's why I drew the normal force acting to the left. That is normal to and away from the wall. And if this was the free body diagram that we would have, notice we have an unbalanced force acting down, but the book is held against the wall, which implies that it's not moving. So we need another force to balance the weight force. And that's going to be the friction force. And in this case, the type of friction is going to be a static friction force. We don't have to worry about what type of friction we have in this unit, but I just want to preview that this is static friction that's preventing the book from sliding down the wall. In this example, we have a baseball player sliding into second base. So we're going to neglect drag, so we don't have to worry about the drag force because he is moving through the air. But we're just going to assume that drag force is so small that we can ignore it. Here's the baseball player. Of course, the baseball player has the weight force acting down, but the player is also in contact with the ground. And so the ground is going to exert those two surface forces, the normal force that is perpendicular to the ground. Here we have a horizontal ground, so we have a vertical normal force. And if the player is sliding to the left, that means there's going to be a friction force acting to the right because friction acts opposite the direction that the player is moving when we have kinetic friction. In this case, the type of friction is kinetic because the player is sliding along the ground. Okay, here we have a rocket car that's accelerating forward. We're going to draw the free body diagram showing all the forces on the car, and again, we're going to neglect the drag force. So here's our rocket car, and the rocket car, of course, has the weight force acting down. And here there's a rocket, so the rocket provides a thrust, and here the thrust is going to be forward, and that's going to be the right based on the picture. The rocket car is in contact with the ground, so we have to worry about surface forces. Here we'll have a normal force acting vertical because vertical is perpendicular or normal to the horizontal ground. And then we'll have a frictional force acting opposite motion. If the car is accelerating forward, that friction force is going to act backward.